From the previous video, we talked about Lesson 16, Analytical Separation. And now we will move on to Activity 17, Gas Chromatography. Before proceeding into the discussion, let me present to you our learning objectives and our conceptual framework. And now let's begin with the discussion.
Good morning everyone. Today's video, we will be learning about gas chromatography. Gas chromatography is a term used to describe the group of analytical separation techniques used to analyze volatile substances in the gas phases. In gas chromatography, the components of a sample are dissolved in a solvent and vaporized in order to separate the analytes by distributing the sample between two phases, the stationary and the mobile phase. The mobile phase is a chemically insert gas that serves to carry the molecules of the analyte through the heated column. Gas chromatography is one of the sole forms of chromatography that does not utilize the mobile phase for interacting with the analyte. The stationary phase is either a solid absorbent, termed gas-solid chromatography, or a liquid will insert or inert support, termed gas-liquid chromatography. So let's proceed to the history of gas chromatography. In early 1900s, gas chromatography was discovered by Mikhail Semyonovich Tevet as a separation technique to separate compounds. In organic chemistry, liquid-solid column chromatography is often used to separate organic compounds in solution. Among the various types of gas chromatography, gas-liquid chromatography is the method most commonly used to separate organic compounds. The combination of gas chromatography and mass spectrometry is an invaluable tool in the identification of molecules. A typical gas chromatograph consists of an injection port, a column, carrier gas flow control equipment, the ovens and heaters for maintaining temperature of the injection port, and the column, an integrator chart, record, and a detector. To separate the compounds in gas-liquid chromatography, a solution sample that contains organic compounds of interest is injected into the sample part where it will be vaporized. The vaporized sample that are injected are then carried by the inert gas, which is often used by helium or nitrogen. The inert gas goes through a glass column packed with silica that is coated with a liquid. Materials that are less soluble in the liquid will increase the result faster than the material with greater solubility. In gas-liquid chromatography, the liquid stationary phase is adsorbed onto a solid inert packing or immobilized on the capillary tubing walls. The column is considered packed if the glass or metal column tubing is packed with small spherical inert support.
Good day everyone, my name is Michael and today we will going to discuss about the principle and application of gas chromatography. The principle of gas chromatography. Components in the mixture are distributed between two phases, one of which is the stationary phase and the other is the mobile phase gas or carrier gas that carries the mixture through the stationary phase. Compound in the mobile phase interact with the stationary phase as they pass through. Due to the differences in properties and structures of each component, the size and affinity of each interaction with the stationary phase are different. Therefore, under the same driving force, the retention time of different components differ in the column, thus moving out of the column in different orders. Application of gas chromatography. Gas chromatography is a physical separation method in where volatile mixtures are separated. Knowing the amount of which compound is in given sample give a huge advantage in studying the effects of human health and the environment as well. Air sample can be analyzed using gas chromatography. Most of the time, air quality control units use gas chromatography with FID in order to determine the components of a given air sample. Since the discovery of gas chromatographic system, the areas of gas chromatography application is ever increasing, which includes pharmaceutical industry, research, medical and forensic, environmental monitoring, petroleum refining and petrochemicals, edible oils, food industry, and pesticides. Now let's go on to the equation of gas chromatography. So high equivalent to theoretical plate means HATP, used to calculate the flow rate by using the total number of theoretical plates and column length. Some application of HATP concept is used in industrial practice to convert number of theoretical plates to packing height. HATP can be calculated with the Van Dimter equation, which is given by HATP is equals to A plus B over V plus CV, where A and B and C are constant and B is the linear velocity. A is the eddy diffusion, term as causes the broadening of solute band. B is the longitudinal diffusion, term whereby the concentration of the annulette in which diffuses out of the center to the edges. This causes the broadening of the annulette band. C is the resistance to mass transfer, term and causes the band of the annulette broader. Next is we have the N is equals to 16 times TR over W squared, where L is the length of the column and where N is the number of theoretical plates and TR is the retention time and W is the width of the dilution peak at its base, in which the more plates give a better resolution and more efficient resolution can be determined by R is equals to 2 times TRB minus TRA over WA plus WB. A relationship between the plates and resolution is given by R is equals to N times 1 over 2 over 4 times A minus 1 over A times 1 plus KB over KB, where the selective A and K is the capacity of factor takes place of the two solutes.
Chromatography techniques. There are 4 main types of chromatography. These are liquid chromatography, gas chromatography, thin layer chromatography, and paper chromatography. When we say liquid chromatography, it is used in the world to test water samples to look for pollution in lakes and rivers. It is used to analyze metal ions and organic compounds in solutions. Liquid chromatography uses liquids which may incorporate hydrophilic insoluble molecules. Gas chromatography is used in airports to detect bombs and is used in forensics in many different ways. It is used to analyze fibers on a person's body and also analyze blood found at the crime scene. In gas chromatography, helium is used to move a gaseous mixture through a column in absorbent material. Thin layer chromatography uses an absorbent material on flat glass or plastic plates. This is a simple and rapid method to check the purity of an organic compound. It is used to detect pesticide or insecticide residues in food. Thin layer chromatography is also used in forensics to analyze the dye composition of fibers. Lastly is the paper chromatography, which is one of the most common types of chromatography. It uses a strip of paper as a stationary phase. Capillary action is used to pull the solvents up through the paper and separate the solutes. Now let's proceed with the detectors used in gas chromatography. There are a wide range of detectors available to measure the output sample, including mass spectrometer, flame ionization, thermal conductivity, atomic emission, photoionization, electron capture, and chemiluminescence. Which detector is picked will depend on the sample being used, since not all detectors will work with all types of results desired. Flame ionization detector, or the FID, is the most widespread and commonly used type of detector since it is very easy to use, dependable, and unaffected by the flow rate or water. The thermal conductivity detector, or the TCD, is one of the earliest and simplest method of detection in gas chromatography. These days, it has become a little outdated in comparison to other methods due to its low sensitivity and flow rate. Lastly is the mass spectrometer, or the MS, which is the most powerful of gas chromatography detection techniques, since it involves the fragmentation, identification, and organization of sample components in order of their mass to change ratio. Gas chromatography is the premier analytical technique for the separation of volatile compounds. Several features such as speed of analysis, ease of preparation, excellent quantitative results, and moderate cost have helped GC to become one of the most popular techniques worldwide. There are 4 advantages of gas chromatography. First, due to its high efficiency, GC allows the separation of the components of complex mixtures in a reasonable time. Second, accurate quantitation. Third, mature technique with many applications notes available for users. Fourth, multiple detectors with high sensitivity are available, which can also be used in series with a mass spectrometer since MS is a non-destructive technique. Gas chromatography has 2 disadvantages. First, limited to thermally stable and volatile compounds. Second, most gas chromatography detectors are destructive except for mass spectrometer.